Okay. Good morning. So we continue the lesson. Hopefully, we can cover this lecture note today if we finalize it. So it is always good because we are discussing about matrix theory rigorously for just the purpose of matrices, not applications right now. So it is also good to know about some other important topics in matrix theory. So today, I don't know, I titled it under the title of Special Matrices, and I want to teach you some kind of operations that are involved with matrices as well. So the first operation we want to discuss today is transposing a matrix. So transposing a matrix is an operation that we apply on a given matrix, and it is extremely simple and useful. But of course, here we will not be able to talk about the applications that much. Might be in the future we will have some time to do that. But what is transposing a matrix? Okay, so assume that you have an m by n matrix, and then transpose of matrix A is denoted by this symbol. So you put a t as an exponent, but it's not an exponent, of course. And this is defined to be an n by m matrix. So if your original matrix is m by n, the product of this matrix, the result of this operation transpose, is an n by m matrix, so that the entry ij of this new matrix is the entry ji of the original matrix. Okay? So in principle, it means that you are interchanging rows and columns. That is, if I want to make it short, this is exactly what you see here. So you see here, this matrix A is a 2 by 3 matrix. If I ask you to find the transpose of this matrix, I mean interchange the rows and columns. For example, 1, 2, 3 is the first row. You write it as the first column. And 4, 5, 6 is the second row. You write it as the second column. The matrix that you generate in this way is called the transpose of your matrix. Okay? And that is clear that I have done the same thing here. For example, let me write it here on the board. So if you have this matrix, A is 1, 2, 3, 4, 5, 6. So A transpose is 1, 2, 3, 4, 5, 6. Yes? And then, for example, if I ask you entry number, for example, 2 or 3, 2, for example, of matrix this. What is that entry? So you go to matrix A transpose and go to the third row and second column, third row and second column, this becomes 6. Okay? But then if I want to find 6 here, I have to go to matrix A, but I have to look at the entry on the second row and third column, yes? Second row and third column is exactly 6 again. So in principle, if I am interested in the ijth entry of this matrix, it means that I can find the ji'th entry of the original matrix. So that is actually the definition of the transpose. But simply speaking, it means that you just interchange the rows and columns. Yes? Is that clear? For example, if I have this one, if I have B to be 1, 2, and 3, what is B transpose? What is B transpose? This matrix includes only one row. You are supposed to interchange rows and columns. So this appears as the first row. You write it as the first column. So this becomes 1, 2, 3. But because this is the only row, that would be the only column. So that would be the transpose of my matrix. Or I don't know, if you have this matrix, square root of 2, square root of 3, if I ask you what is the transpose becomes what? Square root of 2, square root of 3. Why? This is the first row, you write it as the first column. This is the second row, you write it as the second column. So this is something very, very easy. And of course, if you have a square matrix, its transpose remains a square matrix again. Yes, that is clear. So for example, if I have D to be 1, 2, 3, 4, and then if I transpose this is the first row, I write it as the first column. This is the second row, I write it as the second column. Okay, you immediately realize if I have a square matrix something, you can say something about some of these entries, yes? What can you say here? So you see that the entries on the main diagonal remain the same, yes? So this is 1, 1. This is exactly the same thing. So you see, they are not touched at all.
The trace is the same.
The trace is the same, of course, not more than that. Not just the trace are the same, they are actually identical. So the main diagonal remains exactly the same. Why is that? Yes?
It's just flipped on along its axle.
Yeah, here if you want, because when I am looking at the entries on the main diagonal, indices I and j are the same. So when the indices are I and j are the same, so it means if I interchange them, nothing will happen. So if I ask you what is the entry I, what do? You write it as A. You are supposed to flip these two, but when you flip these two, because they are the same, it remains the same. So this tells you that the entry on this ith row, ith column is exactly equal to the entry of matrix A transpose is exactly equal to the ith entry of the original matrix. Okay, so if you have a square matrix, the main diagonal is not touched. It remains the same. Okay, and I think this is also an idea. So what is the meaning of this? Can you tell me? What is this? I don't know how many of you remember this notation. For any matrix A, do you remember what is the meaning of this notation? Yes?
The ith row of AT.
A transpose. So this tells you that the ith row of A transpose, so let us check it here. If I ask you what is the second row, what is the second row of A transpose? This is my A transpose. The second row of my A transpose is this row matrix. Okay? But this is what equal to?
The ith column of.
So the second column of A, but transposed, yes? Because if I ask you what is the second column of A, you will find this. So when I say the second column of A, you get 2 and 5 in a column 4. And then it is clear that 2 and 5 is not equal to 2 and 5 in this form because it is 2 by 1. It is 1 by 2. This is 2 by 1. But if I transpose it, then I have to transpose this, and then I get exactly identical matrices. Yes. So this is a very simple idea. Okay, so I want to give you time because I think these are simple. Mainly you have to do the calculations yourself to understand something. So I want to wait for you to solve these examples, 135, 36, and 37. Okay, so I want you to solve these problems.
Three, six, seven.
Yeah,
Five, three, seven.
this is more or less very simple, but these two might need a little bit of calculations. Okay, so let us solve the problem. So I think the first one is easy, yes? So I have given you three matrices with corresponding orders, and we want to know what is the order of this matrix. So that is extremely simple. So what you need to know is this. So A transpose, what will be the order of A transpose? Because A itself is 4 by 5, A transpose will be 5 by 4. Yes? And then B transpose will be 4 by 6. And then finally, C itself is 6 by 7. So first of all, you can see that immediately this product is possible. And what is the final order? What is that?
5 by 7.
5 by 7. Because when you multiply these two, this is omitted, and then 5 by 6, and then 6 is omitted. So the final answer to this is a 5 by 7 matrix. So that will be the answer to this problem. That was extremely simple. Okay, here I have given you two 3 by 3 matrices, and I am asking you find the entry on the third row and first column of this product. Of course, that's not a big problem. You multiply it and then choose it. But I want you to do it because you don't need all the entries. So it is better just to target and find that particular entry wanted in the problem. So do you remember how we can do that? So here we have A transpose B A. You want to find this entry. But that's a product of three matrices. Matrices are associative. Matrix multiplication is associative, so I can group them in any way that I want to. For example, I can write AT alone and combine B and A together. And then I want to find the entry on the third row and first column of this product. So now I have the product of two matrices. One matrix is A transpose and the other one is BA. So do you remember, if you want to find one particular entry of the product, you will take the third row of the matrix on the left, the third row of the matrix on the left, and you multiply it by the first column of the matrix on the right. So this becomes the first column of BA. Yes? But today we just learned about that. Do you remember what is the third column of A transpose? Sorry, the third row of A transpose is the third column of A, but totally transposed. Yes? That is what we learned today. This we had before. If you are interested to find a particular column of a product, what do? You take the whole matrix on the left and you just multiply it by the corresponding column of the matrix on the right. So this is what you're supposed to calculate if you want to do it efficiently. Okay, so but let us just do that. This is the third column of A. So I come here, the third column of A is this one. So let me just write them explicitly. But I also have a transpose there. But the whole matrix B has to be written down. So it is 1, 1, and 0, minus 1, 1, and 2, and then 1, 1, and 4. And then you have to multiply it by the first column of A. First column of A is 104. And then you have to do this calculation. Okay, so it doesn't matter which way I group them, I will multiply them. But of course, there is a transpose here, so let me just do them in one go. So I transpose this matrix, so it becomes a row matrix, 3 minus 1 and 2. And then I start multiplying these two. So I have to multiply each row by this column. So the first row by that column, 1 by 1 is 1, 1 by 0 is 0, 0 by 4 is 0. So when I add them up, it becomes simply 1. And then I will take this one and multiply it here. So this becomes minus 1 plus 8, it becomes 7. And then I'll take this one and multiply it here. So it becomes 1 plus 16, it's 17. Do you agree? Okay, and then I have to multiply this row by this column. So you know that this becomes one single number. This is 1 by 3. This is 3 by 1. So the product will be 1 by 1, which becomes just a single number. So then I have to multiply 3 by 1, minus 1 by 7, 2 by 17, and add them. So this becomes 30, yes?
Yes.
So the answer is 30. So, I mean, this is a little bit more efficient than multiplying everything. I don't know if I have already talked about GeoGebra, so let us just try to do this calculation on GeoGebra. That is also good to know how is it going. Okay, so I will try to type these matrices in GeoGebra and ask this question. Okay, so here on GeoGebra, if you want to put a matrix in GeoGebra, it's a list of lists, yes? So you just open curly, but let me just give it a name. So this matrix, I will give this matrix a name, as is it here. A is equal to, okay, and then what are the entries? 1, oh, I have to open another curly brackets, 1, 2, and 3. These are the entries of the first row, and then I open another curly brackets, and then it is 0, 1, and minus 1, and then I have this. It is 4, 1, and 2. Yes, am I right? Okay, and then you enter. So this will generate you a matrix, but in GeoGebra, the convention then instead of having square brackets, they have bigger parentheses. Okay, so this is, hopefully I haven't done anything wrong. And then I type B as well. So B is 1, 1, and 0. Yes. Yeah, please correct me if I'm wrong. So then it's minus 1 and 1 and 2. And then we have 1 and 1 and 4. Yes. So this is my B. Now I want to calculate this. I think in GeoGebra transpose should also be defined. Transpose here. So I go to transpose because I want to calculate A transpose BA. So I press this and then I put my matrix in. So this is the transpose of A, but I want to multiply it. So let me put a star between them. And then I put B and then a star, another one, and I put A. Of course, this will give me the whole product. So that would be the whole product. And then which entry we are interested in, if you see here, it is number 3, the third row and the first column. And then if you see that, third column, first row is exactly 30, and that is we found there. I think there is also a way to ask GeoGebra to give exactly that entry. I think you can do like this. The name of this matrix is M1, and then you choose, I think, third row and first column, yes. So you can just put that one, it will give you exactly, so this was my matrix M1. From the whole matrix M1, I am interested in the entry on the third row and first column. So I just intuitively typed that and it worked, okay? But you can find a manual if you want to. So that's also good to be able to do some matrix calculations using GeoGebra as well. Okay, now if we go back to the board now, so this is the probably better question. So do you have any ideas? So first of all, we have three numbers, A, B, and C. They are real numbers and they are satisfying one condition. A squared plus B squared is greater than C itself. And then two matrices are defined in this way. X is this column matrix and A is a square matrix 3 by 3. We want to show, this is of course, if I ask you what this is a matrix equality because X, A, and X are matrices. But this is 0. Do you think this 0 is the number 0 is the 0 matrix? Yes?
0 matrix.
Is it? Yes?
I guess not, because it's a circle.
Yeah, of course, yes, that is one way. But why this the case? Because X is 3 by 1, so X transpose is 1 by 3. This is 3 by 3, this is 3 by 1. So if you calculate the order of this particular matrix, it is 1 by 1. So it is actually number. Yes, it is a number. X transpose AX, if you check the orders as we did, for example, here, in this example, you will see that the matrix on the left is a 1 by 1 matrix. So it is a number. So in principle, this should be, I don't know if I have respected this. Yes. If you see here, yeah, I have used this symbol, which I use for numbers, because I differentiate between the 0 matrix when I want to typeset it in LaTeX. Anyway, we want to show that this equation, which is a matrix equation, represents a circle. And then I'm asking you, can you find the coordinates of the center and the length of the radius? Okay, so how should we do that? First of all, let us calculate this. X transpose AX equals to 0. Let us see. What does this actually give to us? So X transpose means X, Y, 1 transpose. And instead of A, I have 1, 0, A, 0, 1, B, and A, B, and C. And then I multiply it by X itself, X, Y, 1, and then equate it to number 0. Yes? We calculate this. The transpose of this is X, Y, 1. But the product of these two, let us just do it right now. I take this row and multiply it by this column. It becomes X plus A. Yes, because 1 times X, 0 times Y, A times 1, and I add all the results. So it becomes X plus A. 0 times X, 1 times Y, B times 1. Add them, it becomes what? Y plus B. And what will be the last one? So what's the last one? AX plus BY plus, yes, so that is the last entry equals to 0. I have to do it once more. So, but you see that I have 3 entries here. This is 1 row, this is 1 column. I take the first entry multiplied by the first. I take the second one and multiply it by the second one. I take the third one and multiply it by the third one. But you know that I have to add them up, and I don't need to put the sign for a matrix because then it is a 1 by 1. This is supposed to be 0. So you see, it is a very compact form of writing equations. So matrix is also very helpful. Instead of writing an equation like this, you can write equation like that. Okay, but I want to confirm that this equation actually represents a circle. and then I want to find the center and the radius of this circle. So how should I do that? So let me just simplify things a little bit. I have 1x squared here. Let me write them in order. And then you have y squared coming from here. So let me write it immediately here. And then look here, you have x times a, which is ax. You have another ax coming from the last one. When we add them, it becomes 2ax. And then here I have y times b, which is by. Another by is coming from here, so this becomes 2by. And then finally, what is left? 1 times c is left, which is c. So this is the simplified version of that matrix equation. So we want to confirm that this represents a circle. Do you have any idea how to do that? For example, if you simplify everything and if you get this one at the end, then you know that this is a straight line. Yes, but now when I calculated things, I got this equation. We want to confirm that this is actually a circle. How should I do that? So this is also good to know. I don't know how many of you remember, so let me just try to change my color here. So if you have a circle, so this is x and y, assume that you have a circle whose center C has coordinates alpha and beta, and assume that your radius is r. Okay, if I ask you to write an equation for this circle, how do you do that? You would say that, okay, when I want to write an equation for any shape, what I need to do, I need to take a representative point on that shape. For example, I will take it M, and I will write the coordinates x and y, and try to use the geometry of the shape to connect x to y. Okay, that connection is called an equation for your object, yes? So whenever you want to find an equation for an object or for a geometrical shape, you need to take a representative point on that shape with coordinates x and y and try to use the geometrical property of that shape to connect x and y together. If you find that connection is an equation, that equation is the equation of your shape. That is the general idea. So it doesn't matter if you are facing a triangle, if you're facing a line, an ellipse, or whatever. Okay, so what should I do? What is the main property of the circle? What is the geometric property of the circle? It doesn't matter which point I choose, the distance from that point to the center is always r. Yeah, so this means that Cm, wherever this m is, it doesn't matter. As far as this m is on the circle, Cm is r. But Cm, you had it in Math 2C. This is the distance formula. The distance from C to M. It is a square root. The difference between the x coordinates, the x coordinate here is x, the x coordinate of C is alpha, so this becomes x minus alpha to power 2, plus the difference between y coordinates is squared. This square root gives me the length or the distance between C and M. It is supposed to be r. So this is your equation. This is an equation of this circle, but this is common to get rid of a square root sign by squaring both sides. So this is something I want you to at least get familiar with this equation. So this is an equation for the circle centered at C, alpha, and beta, whose radius is r. So this is the equation, an equation. But it seems a little bit different here. So here I have two complete squares added equals to a number squared. This is not exactly in that form, so the strategy becomes clear. I need to ask myself, is there any way that I can transform the form of this equation into that form? If I succeed to do that, then I can read alpha and beta. I can also read R from the equation. So what should I do? Any ideas? So what should I do here? I want to make two complete squares. So you see what are the type of complete squares? One of them involves x only, there is no y here, and one of them involves with y, there is no x here. Okay, so what I do, I will try to do something like this. I will take x squared here, I put 2ax next to it, okay, and then I would write y squared plus 2by, okay. And then if you don't mind, let me move c to the other side. Okay, so this is not a complete square, but I can add something here so that the three terms become a complete square. Yes? So what should I add here to make this complete square? Yes? What should I write here? I want to write something here so that this one, and this one can be written in the form of something to power 2. What? A squared. So I add a squared here, but I cannot just add a squared here. I should also add a squared here to compensate for that. Yes? And then I will do the same thing here. What do? I add b squared here. I also add b squared there. And then these three now becomes x plus a to power 2. These three now becomes y plus b to power 2. And on the right hand side, I have a squared plus b squared minus c. Yes, now if you compare this equation, this is very similar to the general equation of the circle. And if you compare them, okay, what is alpha there? Alpha is the x coordinate of the center. What is alpha in this problem? What is alpha?
It's just a
No,
minus a.
minus a. Because that is, a standard one is minus alpha. Minus alpha, so this plus a is playing the role of minus alpha, not alpha. So alpha is minus a. And what is beta? Minus b. And can you tell me what is r?
A squared plus b squared minus c.
No. Because on the right hand side you don't have r.
The square root of that.
The square root of that. But whenever you take a square root, you have to be certain about something. Okay, that's my question. I actually erased that. You remember there was a condition given in the problem from the beginning that a squared plus b squared is greater than c, and that is the reason. If a squared plus b squared is not greater than c, then I will have problems here. I cannot take a square root sign. What happens in that case, by the way? So here in this situation, I proved for you that this equation represents a circle whose center is minus a and minus b, and this is its radius. Now assume that I do not have this condition. I can still do everything that I have done so far, because when I was doing these multiplications and everything up to here, yes, I still can do it without having that assumption. But the final interpretation will change. So in this case, I have a circle, yes? But what happens if a squared plus b squared is equal to c? It might happen. What happens if a squared plus b squared is less than c? So all the calculations can be done again. So I will get exactly the same equation again. But in the case that this is C, in the case that this is less than C, my interpretation will change. Can you tell me what will happen? Assume that a squared plus b squared is equal to c. Yes?
Then there will just be no circle. Or like the radius will be 0.
The radius, this is a circle of radius 0, so it becomes just one single point, and that is this center. What about if a squared plus b squared is less than c?
It will become an imaginary number.
So it means that there are no circles. So it means that so here, if this number is negative, this becomes a contradiction because the left-hand side becomes negative, but these two are positive. When I add them, it becomes positive, and this is negative. It cannot happen. It means that you cannot find any points whose coordinates satisfy this equation. It means that the graph of that equation is empty. Yes, that's the meaning. Okay. Okay. Any questions? Okay, now let us go back to the slides. So there is a very important theorem. Of course, probably you can guess some of them yourself. So the first one tells you that if you apply transpose on the same matrix 2 times, what will happen? If I transpose the matrix and then transpose it again,
you will get it back.
Take it back. So that is more or less understandable. But now, I don't know, what is the interpretation of that? This is a formula, mathematical formula, but how do you interpret it in words, in English? What does this mean? R is a real number. What does this mean, if you want to express it in words? Yes?
That the transpose of a matrix is associative?
No. It has nothing to do with associativity here. No, just read this formula. This is because, by the way, because you are in math specialization, I want you to be able, by looking at the formulas, I want you to understand the meaning of that formula in words. Yes?
The row of A transpose is the same as the row of...
This is not row, this is R. R is a number.
Oh, okay.
So this tells you that if you multiply a matrix by a number, which becomes a matrix, and then transpose it, it is exactly equal to if you transpose the matrix first and then multiply it by the number. So whatever I told in English, it is actually coded in this equation. So you should be able to read it in that way. Yes? So it doesn't matter if I multiply my matrix by my number and then transpose, or first transpose and then multiply by my number. The results are the same. And in mathematics, you really have to be careful. You are not allowed to take these things for granted. If you change the operations order, you have to be careful if it is working or not. For example, what is the third one is telling you? This tells you that if two matrices are equal, their transpose are also equal, and the other way around. If the transpose of two matrices are equal, the matrices are equal. Okay, but again, I want to interpret this, one of you, in words. Because, by the way, this property and this property, they are called linearity properties. So if an operation is linear, satisfying these conditions, that is easier to work with linear operations with respect to the operations that are not linear. Okay, can you interpret this in English? What does this mean? Yes?
The transpose of A plus B is equal to the transpose of A plus the transpose of B.
So in other words, it means it doesn't matter if you add first and then transpose, or you first transpose and then add. Okay? There is no difference between these, but of course we have to be able to show that. Again, here, it doesn't matter if you subtract and then transpose, or transpose and then subtract in the same order. This is the most important and non-trivial one. Okay? So, can you interpret this now? AB transpose is B transpose A transpose. That is extremely important. So it means that if you want to transpose a product, you can transpose them individually, but you have to be careful, multiply them in the reversed order. So if this is AB transpose, you are not allowed to write in general A transpose B transpose. You have to write B transpose A transpose. Yes? Okay, so let us try to prove some of them. Okay, I think let us prove number 4 and number 6. Others are very similar, but I want you to remember these rules. So how can I prove the first one? Okay, so I don't know, I haven't mentioned. Okay, I have mentioned here that A and B are matrices such that the stated operations are defined. Okay, so for example, A and B should be of the same orders so that I can add them. Okay, so we want, for example, let us assume that A is an m by n matrix. B is also an m by n matrix. Otherwise, I cannot add them. Then I want to prove that A plus B then transpose is equal to A transpose B transpose added. This is my goal. Okay, so how should I prove that? So if I want to prove that a matrix is equal to another matrix, I have to confirm that every entry of the left side matrix is equal to the corresponding entry of the right side matrix. So for example, I would say that let I be a number between m and n, between 1 and m, and j be a number between 1 and n. Of course, I and j should be natural numbers. Then, so if I want, let me start from the right hand side. Then I would say that A transpose plus B transpose okay, let me start from the left. A plus B transpose entry number ij. First of all, am I right in writing it? So I think it's not correct, yes, because A and B are m by n, so when I add them, it becomes m by n, and then T becomes n by m. So this should be between 1 and n, and this should be between 1 and m. Okay, that is, otherwise it doesn't. Okay, so how should I do that? The entry ij of this transpose matrix. So just tell me that you understand what is going on. If I write this, do you agree with me? Yes? So I take this transpose, but I actually interchanged. But this was just a new lesson today. The rest of it is the old lesson. If I ask you what is a particular entry of the sum of two matrices, you will tell me take the same entry from the first matrix, take the same entry from the second matrix, and add them. Yes? But now, if I write this, do you agree with me or not? Instead of this, I write A transpose, then I flip them again. Yes? And then I will do the same thing here. So this becomes B transpose, and I flip them. But what can I write now? I can write A transpose plus B transpose ij. So this means that the ijth entry of this matrix is equal to the ijth entry of this matrix. And this can be done for every I and every j, so this is true. Is that clear? Yeah, this is not very fun, but for the other one, it is actually better. We want to prove that AB transpose is B transpose A transpose. But I have to respect something so that these operations are defined. I want to show this. I want you to feel that where in the proof you see that you have to interchange. It's important, yes? So, but let me just start with something we can do. For example, let me take A to be m by n, and then b is supposed to be multiplied to this from the right. So let me assume that b is what? N by something else, p. Yes? So let us assume that a is n by n, b is n by p. Okay, the first thing I want to prove this matrix is equal to that matrix. I have to confirm that the orders are the same. Do you think the orders are the same? So the order of AB transpose. What is the order of this? We can just do it in our head. What is the order of AB?
M by P.
M by P. So what is the order of AB transpose? P by M. Yes? But let us calculate the order of B transpose A transpose. So what is that? The order of B transpose is P by N. The order of A transpose is N by M. If you multiply them, the order becomes again P by M, and they match. So from order point of view, the orders are exactly the same. Okay. Now, I would say that let I, the left-hand side has this order, P by M. So I would say let I be between 1 and P, and J be between 1 and M. Of course, I and J are natural numbers. Okay, now this, I want you to do it for me, okay? So I will ask you. I want to take this matrix, and I want to look at the ijth entry of this matrix. And I want to confirm that this is equal to the ijth entry of the matrix on the right. Okay, but what is the first step do you think I will do here? So this is AB transpose ijth entry. What can I do? Yes?
You can just write AB and then JI.
JI. So I get rid of transpose operation first. So this becomes AB, but the price that I have to pay is to write JI. And we have practiced about this a lot, yes? This is JIth entry of a product. Do you remember? It becomes a sigma, yes? So do you remember? You start with a sigma. You choose a counter, which is not the same letter. So let me choose K. And then I will always run it from 1, but up to where here in this case? I have written the orders in front of your eyes. K goes from 1 to, yes?
P.
No. N.
N.
The number which is in between, yes?
It's always.
Yes. And then, do you remember? I write A, I write B, but this one, the first one, starts with the first index, ends with the counter. The second one starts with the counter and ends with the second one. Yes? Okay, but you need to have an eye on what you want to prove. You see, I got rid of transpose, but in principle, I need to have transpose, yes? Because on the right-hand side, I have B transpose, A transpose. So I switch back to transpose, okay? But how should I switch back to transpose? It is easy. So I write K equals to from 1 to N. What can I write here? I can write transpose, but the price that I have to pay is to swap them. Yes? And I will do the same thing here. So far, so good, actually. The motivation I did this because I see that on the right-hand side I have transpose involved. So I will take this and then make it a IK. Yes? But now what happens? Can I write this as a product again? I want you to feel that you have to interchange, yes? Because the product, the correct sigma form is the form that these two numbers are the same. Yes, but in this form, this is J, this is I. The middle ones are not the same. But can I interchange these two? Yes, because this one is a number, that one is also a number. I do not have any problems with interchanging numbers. Now, I just want you to feel that why I have to interchange, because it is not in the correct form that I need. The correct form, the indices in the middle should be the same. Yes? So then it becomes A transpose Kj, and then K goes from 1 to N. Yes? But now, is this N also the correct number that I need? Yes, because B transpose is P by N, and it is sitting on the left. A transpose is N by M, and it is sitting on the right. And again, the middle number is N. So what appears here is exactly what I need. So everything is in order. So what can I write this? Can you write something simpler for this now? What is this?
B transpose.
It is B transpose, A transpose, but which entry? IJ. So I am done. I started with the ijth entry of the matrix on the left, and I realized that entry is exactly equal to the ijth entry of the matrix on the right. So I want you to understand these gymnastics of indices. So do you understand that we have to interchange because we want to have the correct form? So that is the proof, rigorous proof for this actually equation. Any questions? Okay, so there are some interesting things coming in. I think these are simple. Using mathematical induction, you can actually combine these rules for more than two matrices. For example, if I give you A plus B minus C transpose, if these operations are doable, then what do? You can write A transpose plus B transpose and then minus C transpose. Yes? I don't know, for example, if I have 2A minus 3B plus 4D, if I want to transpose it, what can I do? In principle, I can transpose this, and transpose that. But there's another rule. Transpose of number multiplied by a matrix is 2 times A transpose. So I can do them quickly. So I can write 2A transpose minus 3B transpose plus 4D transpose. Yes? This can be done. But this is extremely important. So if you want to know something by heart, this formula is that. So what does this mean, by the way? This means that it doesn't matter if I raise to power n and then transpose, or transpose and then raise to power n. It is not trivial, by the way, because raising a matrix to power n is a little bit non-trivial thing, yes? So this tells you that it doesn't matter if you first raise to power n and then transpose, or the transpose first and then raise to power n. Why is that correct? Why is that correct? For example, of course, I want to skip the mathematical induction part. You can do it yourself. So this formula can be actually, what we learned is that AB transpose, if the product is possible, we learn that it becomes transpose of each one of them. But the important thing is that the order is completely reversed. So if I want to write the same thing for 3 matrices, so it becomes C transpose, B transpose, A transpose. Yes, and the proof is not hard. You can prove using mathematical induction, but if I want to prove this only, I would say that I can interpret this in this way. And then I am involving 2 matrices. So this becomes the second matrix transpose multiplied by the first matrix transpose. But again, this is the product of 2 matrices, so it becomes the second matrix transpose, then the first transpose, and then this one. So if you use it 2 times, you can prove this. And using mathematical induction, you can give a rigorous proof. So this means that if I have matrix A1, A2, up to AN multiplied, and I want to take the transpose, this becomes AN transpose, the last one first, and then you can continue this. So you can do that, but in the reverse order. Okay, now let us see what happens if I have an and then transpose. What does it mean? It means that multiply n by a by itself n times and then transpose the result. So this becomes a times a times a and then transpose. Yes? This is the meaning. An, because an is in pair of brackets, it means the priority is with power operation rather than transposing operation. This is the mean. But this I can use that. This is a product. I want to transpose it. I am allowed to transpose them individually, but I have to reverse the order. But in this case, order doesn't matter because even if I start from the last one, this becomes A transpose, and then I can continue here, A transpose, A transpose. Then if I ask you what are you looking at right now, you are looking at a product involving n factors of A transpose. So another name for this is A transpose to power n. So this means that A n transpose is equal to A transpose to the power of n, which is not trivial. So the operations of power, raising to power and transposing are commutative. So it doesn't matter which one you're applying first. Okay, by the way, this is also good to know. Yeah, if I have a negative of a matrix transpose, it becomes transpose and then negative. Why is that? Because negative means R is -1. Yeah, so you can go back here and choose R to be -1. You will get this relation. And of course, this is also something clear for you. And by the way, this is also extremely important. What is the transpose of the identity matrix?
So
It is itself, yes? So, of course, this is not only identity matrix. By the way, can you generalize it a little bit more than identity matrix? Yes? All the diagonal matrices. If you have a diagonal matrix, you transpose it, it becomes a matrix itself. Yes? So, if I have a diagonal matrix, transpose, it becomes matrix itself. I will talk a little bit probably about that later. So let me see, how can I continue here? Yeah, let me keep up to here. Yeah, that is also one more session and then we will finish this. Okay, any questions? You will see that if a matrix has this property, there are other matrices with this property that when you transpose them, it comes back to itself. Those matrices are called symmetric matrices. Okay, a matrix which has this property, it is called a symmetric matrix, and also that also plays a vital role in the matrix theory. But we will come back to it probably. Oh, next week is cancelled. Yes, so after the new year. Any questions? Thank you.